This short video is going to just talk about the assumptions for multiple regression. And one of the reasons why it's short is because there aren't a lot of assumptions for multiple regression. It's a fairly simple and robust statistic that does not have a lot, but there are a couple of things to keep an eye on. One of them is just missing data, as in all research. You want to make sure that your missing data is accurately missing and that there's not too much of it, because anytime something is missing, then it won't be included in the analysis. Second is both univariate and multivariate outliers. The textbook that we use, Martler and Vanetta, particularly emphasizes multivariate outliers and how to do Mahalanobis distance, which I completely agree with. However, I think that examining univariate outliers prior to doing multivariate outliers can be informative for many data sets. It may not be necessary for all data sets, but sometimes you'll find a univariate outlier and then you won't find any multivariate outliers as a result, right? Because it really was a univariate outlier that was the problem. But even if it's just univariate and on a multivariate level, it's not an outlier, I think you can still have a problem if you have a univariate outlier in a multiple regression, because outliers are the major threat to multiple regression. So my suggestion is to both check univariate and multivariate outliers when doing multiple regression. And I generally use 3 standard deviations, sometimes 4 standard deviations, or 3. And in my class for assignments and tests, I'll tell you which, as kind of a cutoff for when something is a univariate outlier. You also want to look at normality. So if you have variables that are skewed, and again, in my class, we do -1 to 1 as typically what's acceptable for skewness on any of our variables. And remember, in multiple regression, all the variables are continuous. So it's both independent and dependent variables that need to be examined for their skewness. And if they are skewed, then they need to be transformed, which your textbook teaches you how to do. Linearity can be a problem, and it's useful to take a few minutes and run a scatter plot and look at the linearity of all your individual predictor variables on your outcome variable. And there's some discussion about maybe you should have linearity between your predictor variables, although I'm not sure that's that important. But what you want to know is if you have a curvilinear relationship of a predictor with an outcome variable, for any of your predictors with your outcome, or you have a hilly, a quadratic relationship, and it's really not a linear relationship, you're not going to find anything, but there might be an interesting relationship that's there, but the multiple regression, it may not be the best analysis. You may need to do something more advanced that can look at relationships that are curvilinear as the assumption of the statistic, which we're not going to cover in my class. You also want to look at homoscedasticity. So if you remember back in the assumption section, it's about homoscedasticity is about there being equidistant, right? That you have a nice blimp of your scatter plots and that you don't have a fan. So a fan would be sad. You don't want a fan of data. You want a nice blimp or hot dog of your data. So for that, you can just examine the scatter plot and look at that. You can also look at something called the Z-pred by Z-resid analysis. So it's the predicted by residual analysis that SPSS will run for us, and your textbook is going to show you how to do that. And you're looking again for a more of a fan type of a pattern or a pattern that doesn't look random. You want nice randomness to that bit of data. There are a couple of assumptions that you should keep an eye on that your textbook doesn't really cover very well. Your textbook does cover a bit of multicollinearity in the chapter on regression. You'll see it talk about multicollinearity, and this is when your predictor variables are too highly correlated with each other. And while rare, this can happen with real data or even one of my fictional data that we use in assignments and tests. And then you have to do something drastic, if you remember back from that lecture, which you could always go back and listen to again. But if you have, say, a correlation of 0.8 or higher, almost anyone would argue at that point that your predictor variables are too highly correlated with each other. Or if you have a tolerance that's less than 0.1, which your textbook also talks about, then your predictors are probably too highly related to each other and you need to drop one of them or create some kind of composite score of the two of them together. So that's one that is not in your list in the back of your textbook. You have that figure 7.27 in the Martler and Vanetta text. that's a list of things, and multicollinearity is not on that list. And I recommend adding multicollinearity to that list in your textbook and actually writing it in, and putting check tolerance and correlation of predictor variables for multicollinearity assumption, and then that'll set you up for that. And then finally, it's not common also, but predictor variables sometimes can have very little variance with the outcome variable. And so they're really just adding noise or error to the multiple regression. So say, for instance, you have a correlation between a predictor and an outcome variable that's like 0.05. Like, it's just so small, right? That it's really not telling you anything about the outcome variable. You might make a decision prior to running the regression to drop that variable and not include it because it ended up not having any prediction power, and it's just going to add error to your larger, bigger multiple regression question that you're trying to answer. So those are a couple things that you might add to your textbook and write in and have ready for the future. Multiple regression is the most common analysis that I see students doing in their dissertations, so you might use that page again one day.